for your kind introduction, and I want to thank the organizers for the invitation to come here. I'm so pleased. It's my first time here, not the first time in Japan, because I also have a part-time position at Tohoku University in Sendai, but I'm very new actually to Ising Machines, and so this is something we've done only the last few years. Let's see if it moves now. No, it does not. Okay. So I want to highlight the main inventor of this technology is Artem Litvinenko, who joined my group some 2 or 3 years ago. But I want to highlight the team that works on this. This is Roman Kimin, Ahmad Awad, graduate students Victor Gonzalez and Roman Ovcharov. I don't need to introduce the topic much to you, but I will say that we focus on Ising machines for combinatorial optimization problems. So let's just say that you all know why we're doing this. We want to carry out these calculations that are very hard to do brute force. There are good approaches to do it in software, and there are hardware Ising machines available. And the idea is that you want to find a system, some type of system in software or in hardware that can be governed by a Hamiltonian that you then program with a coupling matrix and maybe a local bias vector, and then you hope that your system will find the local solution. And the best known approaches for this, I think, is the D-Wave system we heard earlier today, which is, you could say, slightly easier to make. It's a fantastic technology. I'm very, very impressed, but has come much farther than generalized quantum computing in my opinion. And it's because it's slightly lower demands possibly on making an Ising machine than a generalized gated quantum computer. But it's easier to make something classical, and that's been also done in Ising machines by NTT, for example. And this is where we are trying to operate as well. We're going to do something completely classical that still contains a lot of engineering. So rapidly, I hope I'm not saying something that's wrong here, but D-Wave has had some tremendous technological development, and now I think have 5,640 spins with a connectivity of 15, and I think there's even better in the pipeline. But as you've heard in other talks also, this is not an all-to-all machine, so it has some pain points, you could say, if you want to solve combinatorial optimization problems. That is why there has been such interest in the coherent Ising machine, especially here in Tokyo or in Japan, because it comes from NTT research, primarily from Japanese researchers. And you are probably aware of a lot of these papers. Don't know if this is running out of battery or not. No, I just had to press harder. So they showed first some 100 spins and then 2,000 spins. And one of these papers, taking this from one of the papers where they introduced an FPGA to control the pulses. They have a storage ring of optical pulses. So this is an optical fiber of about a kilometer long. And then they pump it with a second harmonic such that the pulses here, they will get gain if they are either in phase or out of phase. So their spins will be optical pulses with a phase state. And then they siphon off a little bit of energy here and detect the phase, let the FPGA store that in a vector of the phases. The FPGA has the matrix for the matrix vector multiplication, and then you get out what the coupling, what the vector should be, what the element should be that you should feed back to a particular pulse when it passes through the second nonlinear element. So then you add energy in or out of phase with that pulse in proportion to the result you got from that matrix vector multiplication. And then the pulses, they just live inside this optical ring, and all the computation, all the interactions are done extrinsically here in the FPGA. After some circulations, there's the optical pulses feel gain, and they start to exist, and then they exist with a well-defined phase state. And after a while here, the problem is solved. After some 100 round trips or so, all the phases they have decided on what phase they want to be on. They have since made a 100,000 spin Ising machine based on this principle. So this machine here solves a MAXCUT problem with FPGA, a whole bank of FPGA. So that's one of the constraints of this technology, that you're pushing the You can have all-to-all connections, which is excellent because 100,000 spins with all-to-all connections is fantastic in hardware. But the constraints then fall onto the FPGA bank. I think they use some 56 FPGAs to do all those multiplications, and that's where the bottleneck will end up, as that will scale as n squared. So there are definitely some problems here that you need 5 kilometers of optical fiber under temperature control, and that draws power and it's expensive. And but they have really solved the connectivity problem, scaling up to a high number of spins and fast solutions. And they will continue to do this. And this is where we, or Artem Litvinenko in my group, I would say, identified that we can make this with spin waves instead. So here is an example. Here is a YIG film. Yttrium iron garnet is a ferrimagnet, insulating ferrimagnet with the lowest spin wave damping known to man. Still some damping. So when they get injected here with a copper wire, they propagate 7 millimeters, and then they lose about 35 dB of power. So there's considerable damping if you compare with optical fibers, of course, where there's basically it's none across this distance and very little over kilometers of distances. So damping is an issue, but not a big problem. You can amplify that back easily. So the benefit of it is that okay, I thought it would start here. It doesn't matter. Let's move. The idea then is that we will translate the optical approach here to where the frequencies are optical, so terahertz, several tens of terahertz or more. And then we're going to go into the microwave domain where we're at 3 gigahertz. Then everything becomes so much easier. Off-the-shelf components can be bought. You don't need kilowatts, you need a watt or less. And also the performance improves because it's the optical frequency, the speed you could associate with the optical frequency is not used here. So microwave frequencies have much lower phase jitter than what you need to keep the very, very high frequency of the optical pulses under phase control. So the temperature stability and the signal to noise is so much better when you operate now at microwave frequencies. There's the other benefit that was the immediate one that we identified, and that's that the group velocity of spin waves is super slow. So 3 to 7 orders of magnitude slower than light, which means that you can miniaturize this now. So a group velocity of 100 meters per second means that you can use millimeter-sized waveguides. Now, this then leads to miniaturization. It's a thin film technology. We can pattern these YIG films. We can get millimeter dimensions instead of kilometer dimensions. Now, the film we picked is not optimized. So spin waves are highly nonlinear. That's why the group velocities can be so immensely different. And the group velocity we're going to use is not particularly slow. So 25 kilometers is unfortunately quite high. So we will not be able to miniaturize this so much in the first step. But this is what I will show because it's the first attempt ever, and we got some results out of it. If we translate directly from the coherent Ising machine, they have 20 spins per meter, and we should have then 10 to 4 more per meter. So we should have some 1,400 spins fit into this. But we're not even close because we're not using photons. Spin waves are highly nonlinear, and they come in particular bands. So, and these bands depend on magnetic field, and it's a whole research topic on its own from the Second World War. Radar technology uses these YIG materials for all kinds of devices. So we have to look at the transmission of spin waves, and here we see that there's a spin wave band. The 3 dB bandwidth is 60 megahertz, and this is the only bandwidth we can operate with at 3 gigahertz. So that sets a limit to how fast we can ramp up the pulses and how fast they will decay. So 1 over delta F here gives us 60 nanosecond ramp rates then. But there are additional issues. The nonlinear dispersion will make the time delay having, the speed will be higher at low frequencies than at high frequencies. So the time delay will be longer for the higher frequency ones than the lower ones, and that leads to spreading of the pulses. So if we add that together, we're going to start with some bandwidth limited pulse length, and then we're going to end up with a bandwidth plus dispersion limited bandwidth pulse length here, when we have to fit those into the waveguide, and that's what we end up with. 6 pulses is probably what we can fit based on these measurements. So if we do that, if we fit 4 pulses, they are well separated. And if we fit 8 pulses, they are barely separated. So this agrees very well with what we predicted from the measurements. But this is what we're going to use. So now we have to phase-binarize them. So in the coherent Ising machine, they pump the optical fiber with an optical element such that there will be gain on the fundamental frequency, but at 2 different phase states. And we're going to do a similar thing. We're going to use an amplifier that is meant to amplify the fundamental frequency, but then we're going to pump it with a second harmonic of that frequency. And the amplifier then will, you can view it naively maybe as the amplifier will choke with the frequency of the 2F signals. So it will be better at amplifying. It will be better at amplifying the fundamental frequency at phase states where it's not choked by that 2F. Or in other words, this is a parametric amplifier. It's parametrically pumped by an external signal at 2F, and that leads to a phase-sensitive amplification, which is substantial here on a log scale. And this is definitely big enough to get to well-defined phase state, because when we run the complete machine now, and we use an oscilloscope to trace out, the oscilloscope can trace out the individual oscillations here. You don't see it because of the resolution, but then MATLAB can just tell you immediately, is this in phase or out of phase? And this is out of phase red, this is in phase blue. This is the random state. We're not doing anything to the system. The system, just as the coherent Ising machine does, the system starts to self-oscillate when there's gain, and it self-oscillates on well-defined phase states like this. So that works. Now we have to control it. We have to program this Ising machine. We're going to program the absolutely most simple matrix we can think of. This is nearest neighbor, even unidirectional negative coupling. So these are just 4 elements of -1. If you want to translate that into a MAXCUT problem, these are the couplings. They are unidirectional. And if you saw that random state that we started out with, it corresponds to a cut like that. The actual solution should be a cut like that. So let's run the machine then with this coupling. And the way we implement this coupling is not with FPGA. This is our very first attempt. So no FPGAs at the time. Instead, we're going to have a coupling cable here that is some 20 meters long, and it has a delay time of 68 nanoseconds, which corresponds to 1 pulse moving 1 step, to the pulse train sort of moving 1 step. That's 68 nanoseconds. So when a pulse is injected here, we siphon off 10%, let it delay 1 pulse transmission, get it back into a coupler here, where we again just take 10% of it and combine it with another picked up pulse here, and those 2 energies then add at this point. So we're coupling the first pulse we injected here. That pulse state is now coupled to the pulse that we picked up 68 nanoseconds later. So it's a direct physical interaction in the electronic part of this Ising machine, but it's not FPGA controlled in any way. And if this animation now runs, I haven't tried it here. Let's see if it does. This is the original state, and the machine is now running. And those 2 spins are both affected, but the proper solution wins. And after a few round trips here, we have the antiferromagnetic state that should correspond to the solution. And I think the animation will restart, I think. We'll see. Now it restarts again. So you will see that the pulses again are affected because they want to be nearest neighbor antiferromagnetically coupled, and this pulse decides to switch earlier, and hence when it becomes red, this pulse no longer has any reason to be anything but blue. We can do this at 8 spins as well. So although they are very close to each other, we can do the same type of matrix, the same type of problem. Here we just initiated a problem with all ferromagnetic coupling, so the spins are just pointing up. And then the system will start to not be happy with that, and it starts to do things and flip around a little here and there. But as you see, after some time, we end up also here with an antiferromagnetic coupling, which we should get from this antiferromagnetic coupling. And it is the solution to this particular MAXCUT problem. We can run this repetitively. So this is what it looks like in a typical run. I mean, you can run it with well-defined pulses and then turn on the coupling, or you can have the coupling be on from the beginning and then turn on the gain. And these are different. This will correspond to different annealing schemes, actually. But I don't have time to go into the details of that. But in this case, we ran with the coupling on and the gain off. So here the gain goes on, and then the pulses start to develop. And they develop, since the system is promoting phase states, they will grow in amplitude with a well-defined phase. And then they were not getting the solution here, so they start to struggle a little bit, and here is the actual solution. So the time to solution here, if you want to, from the start here, is 3.4 microseconds in this case. So that's our very first demonstration. 8 spins is definitely not particularly impressive, but it's the first jig film we had lying around, and the proof of principle works. So if we now go to the literature, which is full of spin wave electronics, believe me, we can take one work here from 2014, so 10 years ago. They made much thinner films. Our film was a micron thick, and that's why it had high group velocity. If you take a very thin film, damping goes up. But after some development, people managed to get the damping low, also in very thin films. And now the group velocity is almost 2 orders of magnitude, 1.5, or more than 1.5, almost 2 orders of magnitude lower, so 600 meters per second. A decay time of 550 nanoseconds, and let's say we can accept 60 dB of loss, which we can re-amplify. You have to do a little bit of design and calculations, but you will end up with the longest delay line you can use is 2.7 millimeters, and that can hold 760 spins in this case because the speed is so much lower. And then in the first demonstration, we just had a film, so it was 5 by 10 or something like that millimeters. But even a 1 micron track is essentially macroscopic. So you will get the same type of spin wave propagation if you have a width of 5 millimeters or if you have a width of a micron. If you go well below this, you can have tracks that are 50 nanometers, but then damping goes up again a lot and things change. But we believe that 1 micron tracks should be fine. If we separate it by 10 microns, we should not have any crosstalk. That could probably, relax this a little bit as well. So within a distance of 1.5 millimeters, we should be able to have 150 tracks. And it's not a coincidence that we chose this, because this way we get up to 14,000 spins. So it's possible to fit the same number of spins as in the coherent Ising machine in an area that's 2.7 times 1.5 millimeters squared. So instead of a 5-kilometer optical fiber, you have a chip that doesn't take up any space, really. So this is what we do fundamentally now with research funding, trying to implement this, and it's going to be a very long project, and a lot of interesting spin wave physics will come out of this. Not necessarily the best implementation, but possible to do, I think. Instead, we're going to move to surface acoustic waves, which is a much better known technology in industry, because surface acoustic waves are used in a lot of filters. Spin waves are not used so much anymore. So instead of having the spins, the magnetic moments, doing their oscillatory movement. We're going to have actual atoms in the crystal doing Rayleigh waves on top of the surface of the lithium niobate crystal. So this is a surface acoustic wave delay line that we bought from eBay. What are the good things? It's a linear dispersion, so it's better than nonlinear dispersion. It's insensitive to magnetic fields, which is better than being sensitive to it. It's not as miniaturizable, but so we can't get down to those extreme small dimensions. But for other purposes, it's likely better. So let's see. Yeah. This is now the second design that we made. So now we have removed the coupling cable, and instead we put an FPGA here that we program. And we need a few more elements then. So we need the FPGA, we need a phase detector, because now the FPGA needs to know the phase. The cable doesn't need to know the phase, it just transmits. But the FPGA needs to know the phase. So we have to have a fast phase detector. We need to have a digital attenuator if we're going to turn on and off couplings from the FPGA. Of course, it could be just an on and off switch, but we're going to use a digital attenuator because we also want to do weighted problems later on. And a phase shifter would be nice to have to be able to change the sign of the coupling if we want to do that. Yeah, that's what we set out to do. The first part of the spin wave talk is published in Communication Physics. I hope you saw that there was a link there. Here, this paper is on arXiv, also being evaluated in Communications Physics. So we do the same thing. We measure the S21 parameters. We find out now that at 300 some megahertz, we have a bandwidth that's relatively much wider, so 100 megahertz. We should have a perfectly linear dispersion. It's not perfectly linear. There's a little bit of change here. So over the time delay of 12 microseconds, there's a 45 nanosecond difference if you look over the bandwidth window. So there is some issue from the dispersion as well. So this should give us pulses, ramp rates of 10 nanoseconds, so this should broaden the pulses by some 45 nanoseconds. There are other limitations, though, and the one is the phase detector. So it has some response time, 50 to 70 nanoseconds. And it's also questionable whether if you make the shortest pulse and then let it, that would be 3 periods, and you then let it spread out. It's not obvious that the phase detector will operate with that. So we pick slightly longer pulses, 32 periods, and that works very well with this phase detector. That gets us 58 pulses. We're going to use 50 of those for Ising spins, and we allowed ourselves 8 sort of buffer spins if the FPGA would be slow for some reason during the multiplication or something like that, but that was not an issue. But we're going to do a 50 spin Ising machine. This is what it looks like. Here is one such pulse, about 32 periods of that 300 some or 320 megahertz signal. And this is a blown up scale. Every spike here is actually one such pulse. So they're separated by about the same spacing as well. So that works well in the waveguide. Now we're going to solve a 50-node MAXCUT problem. So we're going to have on and off connections, negative connections, and this is the graph for the problem, and this is the matrix where a black dot is a -1. When we let the system run with this, it looks like the following. So in the top curve here, you see off being no gain in the system and on being gain in the system. So then it takes a while for them to build up, and they start to interact, and their amplitude is still quite weak, but they start to interact through their phases. And you could say already here, you actually have the solution to the problem. But the temperature is actually going down. If you look at how the coupling size is in proportion to the amplitude of the pulses. The higher the pulses, the lower the effective temperature. So the system is at high temperature here and freezes here. So the temperature is still on here, so it fluctuates a little bit, and those two spins make up their mind eventually and go back to the fold. And after 400 microseconds, we have a stable solution. The energy is not changing after that. It's interesting to look at how this depends on overall global coupling. So here is when we put an additional damper that we manually could turn on, and could change the number from minus 60 dBm, effective damping it turned out to be, minus 60 dB, probably I would say. And here is just more or less random solutions, random results. We ran the system for 1,000 times, and we collected the end result, and this is the energy of that. But when we crank up the power a little bit, so 1 order of magnitude, 2, and so forth, you can see that the solution is tightening up and it's going to lower and lower energies. But still, we haven't really gotten to any optimal solution yet. Here we are doing that though. So here you can see that about 20% in the cases we have the lowest energy. And here it's 50, and here's 85, and here's 100% out of 1,000 attempts. And then we're starting to couple too strongly. So here it's 81, and here it's 50 again. So here we are entering into local minima. And here the system is at too high temperature, so it's not stable. So you would like to operate either here if you are happy with this annealing scheme, or you would move around this point if you're not happy with it and would like to have additional, shaking the system additionally. So it works also in surface acoustic waves, delay lines. This is, as I said, this is about to be accepted, I think, in communication physics. Stuff that has not yet been submitted is when we use this digital attenuator to do weighted problems. So first we just did MAXCUT. But if we have more bits, we can do more things. If we have local bias, we can do Travelling Salesman Problem. So this is something that the grad student Victor Gonzalez looked into. With 50 spins, you can do 7 cities. So this you can solve by eye, more or less. But this is what Victor Gonzalez thought was important, to find the shortest route between Spanish wineries. So this came in handy when we had a conference in San Sebastian. So this is the route that the system actually found. So we can solve TSP problems of this tiny size on this particular machine. And then we did graph partitioning. These are 50 points, random points. They're divided up into 2 partitions, and then we can use another one and divide it into 4 partitions. So that also works. What we've done a little bit recently is to take several of those delay lines and daisy chain them to see if we can build bigger machines. And here's just on the microwave side, everything works nicely. So these are the pulses. I can't really go into what this is, but we can fit about 300 spins now into 4 such daisy chained lines. Our FPGA development is very slow, so that's why we can't really operate it yet. But for ultimate scaling, you can go to the literature. So before CMOS solved all our problems, basically, people were interested in analog logic. And this is a paper from 1975 where they demonstrated very long delay times in surface acoustic waves. So they had a center frequency of 83 megahertz. And the bandwidth that covered most of that, 65 megahertz. And they claimed they could get 60,000 pulses into that. And an insertion loss of 63 dB, close to what we also accept, because we think we can efficiently amplify back 60 dB. So if we take those numbers from the literature, 60,000 analog bits of data should respond to, maybe, if we allow 6 periods in a pulse, something like that. Let's say we have 10,000 Ising spins then. If we have 10 such delay lines in series or parallel, we have, again, 100,000 spins. So also with this technology, it should be possible to scale up to the coherent Ising machine number of spins. And then we run into the same FPGA bottleneck as they do. Other directions we're working in is, there are other delay lines. Bulk acoustic waves are faster. So these are from, you can buy those. They are a little bit more expensive. We have tried two types, 1.7 gigahertz and 2.8. We've characterized them and just estimate that we should be able to fit 5,000 or 3,000 spins in there from our measurements. And then the time to solution would speed up a lot. If we take the paper values of, or the spec sheets of these bulk acoustic wave delay lines, we should be able to fit 1,500 and 400 spins here, getting 2 microseconds to a solution. And we have checked that we can get 1,000 spins, for example, into, I don't remember which one of them it was now, but we can get easily over 1,000 phase-binarized spins into that. So we can solve MAXCUT problems of the type I first showed you with cables. We can solve that with over 1,000 spins, but the FPGA development is lagging. This would be interesting, for example, if you want the fastest possible solution. For example, Toshiba's simulated bifurcation machine, they use that for, or they want to use that. They've demonstrated high-frequency trading with it, for example. So they have, in the first demonstration, they had 150 microseconds time to solution. I think they now claim that they have 30 microseconds, but maybe they have reduced the number of spins, because I don't think anything really changed between those two. So it's a function of spins. But we are, if we use a delay line like this, we are 2 orders of magnitude faster and with more spins actually than they do. So really high frequency trading could potentially benefit from the fastest possible Ising machines. But there are more interesting things one can do also if one has the time and the resources. So some of the things we really want to do but haven't had time to implement in FPGAs yet is higher order couplings. The chairman of the session showed this morning that QUBO is a limitation. If you can do polynomial couplings instead, higher order interactions is very, very interesting. And we think that's just something you have to do in the FPGA. Well, we don't think so. It is something you just do with the FPGA. The system doesn't care what you do with the pulses otherwise. So that's something we really want to do. Something else we have demonstrated is that we can do multi-valued spins. So conventional phase binarization, what I showed you here with a phase-sensitive amplifier, gives you 2 phase states. But people are looking into multi-valued spins, both theoretically, and this is actually with another technique, Nikhil Shukla at University of Virginia, sorry for the cutoff here, but he shows with other types of oscillators that he can get multi-valued spins. And we have demonstrated that. Maybe I should have shown some results of that, but by playing with a 3F pumping instead of 2F pumping, you can get the same behavior. It gets weaker and weaker. So for example, here, it's just, this is a cartoon, but you know, if you do 6, if you want to have 6-fold, you're going to have less stability of the spins. Just naturally, it will become that way. So, and if you go all the way to no binarization, allowing for continuous spins, which is sometimes called an XY model, but I think it is what the chairman called a hypercube this morning. So I added it here. Potentially, we could implement what you suggested this morning, Helmut, that we could maybe do random key optimization using an approach like this. So with that, I'm actually ahead of time. I thought I had too many slides, so therefore I spoke a little fast. But I want to thank the team again. If there's something, did I put it here? No, maybe I put it here, yes. So we've done classical Ising machines for combinatorial optimization, and we think we can get to 100,000 spins both in the spin wave and the surface acoustic wave domain. Maybe that is not what is the most important thing to do, because we're going to run into the FPGA bottleneck. But very fast Ising machines could maybe be interesting for example, high frequency trading applications. And then listening to the talks this morning, higher order interactions and random key optimization sounds super interesting if we can implement that in this technology. And our bottleneck as a research group is not the hardware. So we have demonstrated now 8,000 spins, and there is not a problem to demonstrate 100,000 spins in other types of technologies that we're looking at. But the FPGA programming is the huge bottleneck. Here we'll be very happy if you would join us in a research group or collaborate. And we even, you shouldn't be shy if you think this is a business opportunity. We think it is. Let us know if you're interested in any such things. So with that, I thank you for your attention, and there's apparently plenty of time for questions now.
Thank you for a fascinating talk. Are there any questions?
Thank you very much for this nice talk. At some point, like you were discussing that you could improve the accuracy of your model by increasing the coupling strength, was it? And then at some point, if you were putting too much power, it would start like to decrease.
Mm-hmm.
So my question is this like for each problem, this power would change, or is like based on like your designs? So like,
if this optimum will be problem dependent.
Yes.
I don't know. We haven't evaluated that exactly. If you go to the paper here, Artem has put in a lot of data.
Mm-hmm.
But I don't think we have done exactly that. My hunch is that it's only weakly problem dependent.
Yeah.
The type of accuracy that we get here, everything is green and nice and 100% solved, is for this random matrix. We didn't pick it, so it's a random matrix, but it's a matrix of some density. So in the paper, you will find that Artem went through a whole range of densities and hundreds of different random matrices, and also well-defined sets from literature, because the referees asked for that. So in the updated, maybe in the published version, there will be all of that data. And then, of course, this also drops, and we're not going to get 100% accuracy. You could maybe consider this a fluke. It shouldn't be 100%, but it's within 1,000 attempts, it happened to be 1,000 correct ones. Yeah.
Okay, thanks.
Yeah.
Any other questions in the audience? Paul?
Yeah, very nice talk, interesting things. I got confused when you were talking about your phase-sensitive amplifier that you're driving it to omega. So it's a parametric amplifier, but it seemed to be just like an off-the-shelf linear amplifier from mini circuits. So,
yes.
So where's the non-linearity coming from that gives you the parametric amplification?
So that is an excellent question, that it just has to be explained like something nonlinear is happening inside the pre-stages of the amplifier. So we don't know. So if we knew, we would solve that problem at all the frequencies we have. So I can't tell you exactly what's going on inside there.
Could you deliberately choose a microwave amplifier that has stronger nonlinearity and is designed to be used as a parametric amplifier? That's
okay. That would be a solution. Yeah. So off-the-shelf amplifiers that we have tried worked for 3 gigahertz and worked for 300 megahertz. That one particularly, and did the job. So 20 megahertz, no, it didn't work. So at 20 megahertz, we have our own solution, which is a little brute force that works at 20 megahertz because it's so slow. But at 3 gigahertz, it would not work. So having an actual parametric amplifier that does exactly this, I guess. But microwave electronics is not really my field, but I think we couldn't find it off the shelf so easily. We would have to design it.
May I have a very quick another question?
Knock yourself out.
So your local fields that you call a Z-man term, how do you implement them? Are they in the FPGA or do they get implemented somewhere else?
So in the spin wave version, we implemented it in some way that I've forgotten now exactly, and that wasn't very good. But in the FPGA, it's trivial. So the FPGA handles it. Yeah. And that's how you should. I don't think we should be playing with cables unless you could offload some of the couplings. Let's say you have a, and these are things I want to try that the group is not so interested in. But let's say you could have a network of something that is just static, that gives you a template of negative couplings. And then on top of that is, that's going to be a restriction. But on top of that, you're going to have an FPGA that lives with that restriction, but doesn't have to do at all as many computations. But I'm not sure it's going to work. We're playing around.
Any other questions?
Thank you very much for very impressive talk. So my question is actually that about the integration of your system. So your system looks like something like wiring with a discrete or component, and also the FPGA, and also some other component. So is it possible to make the integrated circuit using, for instance, MRAM technology, fabrication technology, something like that?
So not MRAM is not necessary, but all the microwave parts of this. Let's see if we find and take this one.
Yes.
All the microwave parts here are discrete.
Yes.
So ideally, you wouldn't, in a product, it would not be discrete. You would integrate this entirely. PCB.
Yes, okay.
But this is really a bird's nest on the desktop.
But in the future,
it's not so beautiful, put it that way.
But in the future, yes, you can make the integrated circuit, right?
You could potentially do this as an RF,
but not necessarily.
But sorry,
not necessarily to make such kind of
PCB solution would be sufficient.
Okay, good. I see. Thank you.
And the jig then would be bonded. You would fabricate, and that's what we're doing. If we pattern the jig films into tracks, we would have individual antennas or transducers on the tracks, and that would have to be, wire bonded to whatever RF CMOS chip you have. So that's it's a heterogeneous integration that way. Yeah.
Any other questions from the audience? I ran out of. Actually, I have a question.
Yep.
Unless I'm wrong, the FPGA, all it does is a matrix vector multiplication, right?
Yes.
Have you considered maybe leveraging other hardware than FPGAs? Like, for example, there's a chip by Grok that is designed originally for machine learning applications, but it has a much bigger bandwidth, or TPUs of Google, or Trainium chips from Amazon, or even there's S2 Corporation that makes optical chips for vector matrix multiplication that might be able to allow you to scale even further.
Yes, and there are resistive networks also. Maybe that was one of the technologies you mentioned. I don't know. So yes, it's our own limited bandwidth and resources. But and right now we're happy playing around with FPGAs, although we're so slow developing the code for that. But yes, to overcome the FPGA bottleneck, you have to be innovative on the matrix vector multiplication. So it would be super interesting to just demonstrating it if you have any suggestions for that.
Okay.
Definitely.
Well, let's thank the speaker again.
Thank you.